This video conveys helicopter capabilities and limitations. What the helicopter can and cannot do. Subjects covered include the flight controls, aerodynamics, hovering in and out of ground effect, emergency procedures, weight and balance, and density altitude. There are 4 primary flight controls. The cyclic, flown with the right hand. The collective, on the left side of the pilot. This one includes the throttle. And down below, we have the anti-torque pedals. Through manipulation of these controls, the pilot can fly the helicopter. When the pilot moves the cyclic forward, this tilts the rotor disc the same direction. This will redirect lift and thrust, moving the helicopter forward. As the cyclic is moved backwards, the rotor disc tilts to the rear and the helicopter moves backwards. The same is true for movement to the left and to the right. The collective, at the pilot's left side, controls the up and down movement of the helicopter. As the collective is raised, the pitch of the main rotor blades is increased collectively. More lift is generated, and the helicopter goes up. When the pilot lowers the collective, lift is reduced, so the helicopter descends. The throttle is also located on the collective. In turbine helicopters, the pilot uses this during startup and shutdown of the engine. A governor controls proper engine RPM during flight. The anti-torque pedals control the thrust of the tail rotor. The tail rotor counteracts torque created by the main rotor and keeps the helicopter from spinning. The anti-torque pedals also provide directional control, left and right, when the helicopter is in a stable hover. When the pilot pushes the left pedal, the helicopter rotates to the left. The right pedal causes a turn to the right. A condition called ground effect generally improves the capabilities of helicopters. Simply put, when a helicopter is within 1/2 rotor diameter from the ground, it is called hovering in ground effect, or HIGGE. A cushion of air has been created between the ground and the helicopter, increasing lift and reducing power requirements. Providing the surface is relatively smooth and level. Rough terrain, long grass, ridge tops, or pinnacles may reduce or even eliminate the advantages of ground effect. Once the helicopter exceeds the 1/2 rotor diameter distance above the ground, the cushion of air dissipates and is now hovering out of ground effect, or HOGE. To maintain a hover, the helicopter must now use considerably more power, reducing its effective payload. The helicopter is much more efficient when it can use in-ground effect sites for takeoffs and landings. If you must use an out-of-ground effect site, the number of people or pounds of cargo you can carry may have to be reduced drastically. A normal takeoff consists of bringing the helicopter up to an in-ground effect hover and translating the helicopter into forward flight. Additional lift is created as the helicopter moves from the turbulent air created from hovering to undisturbed or clean air in forward flight. This is called translational lift. Translational lift occurs at about 16 to 24 miles per hour. Translational lift will also be produced when hovering with a 15 or more mile per hour steady headwind. The wind blows the turbulent air away and provides clean air and more lift for the helicopter. This is why pilots prefer to take off and land into the wind. When the helicopter must hover out of ground effect to enter or leave a confined area, or to clear a tall obstacle without the benefit of translational lift, this is called a maximum performance takeoff or landing. During this maneuver, the helicopter is totally power dependent, and margins of safety are reduced. So whenever possible, try and avoid these types of landing areas. What are the helicopter's capabilities in the event of an emergency? An engine failure, for instance. Engine failures in turbine helicopters are very rare. However, should one occur, a helicopter is capable of auto-rotation to a safe landing. During powered flight, air flows through the rotor system from the top and out the bottom. Helicopters have a freewheeling unit which automatically allows the main rotor to rotate freely if the engine fails or there is some mechanical emergency. The rotor system then maintains flight RPM by reversed airflow. The pilot has full control of the helicopter during the maneuver. Each helicopter model has a chart called the height velocity diagram. This chart shows the combination of airspeed and altitude from which a safe auto-rotation can be made. The safest flying is done above 500 feet and at cruise airspeed. In the event of any auto-rotation, remember to assume the emergency position.
Density altitude. By definition, density altitude is pressure altitude, or elevation, corrected for temperature and humidity. It can have a profound effect on aircraft performance. Air is said to be thin at higher elevations. There are fewer air molecules per cubic foot at 10,000 feet than at sea level. As altitude increases, air density decreases. Lower atmospheric pressure allows air molecules to move farther apart. As temperature increases, air density decreases. At higher temperatures, energy excites air molecules to move farther apart. There are fewer molecules in 1 cubic foot of warm air than cool air because air expands as it is heated. When air density decreases, density altitude increases. As you go up in altitude and temperature, density altitude also goes up. When density altitude goes up, helicopter performance and capabilities decrease. The rotor blades have fewer molecules to grab, and the pilot must increase power. At lower density altitudes, such as at sea level on a cool day, the rotor blades move through dense air, have plenty of molecules to grab, and create maximum lift at lower power settings. During warm summer months, plan helicopter missions for early morning, when the air is cool to maximize the performance of the helicopter. If you add hovering out of ground effect, or hoagie, to your mission, remember, when it's high, hoagie, and hot, don't expect to carry a lot.
Manufacturer specifications dictate the amount of weight helicopters can carry at any given altitude and temperature. The pilot determines allowable weight based on the current conditions. Loads are calculated from the aircraft flight manual. This weight or payload must not be exceeded. Accurate weights of passengers and cargo are an absolute necessity for the pilot to properly load the helicopter. Once the allowed payload has been determined, it must be balanced. If you draw an imaginary line through the helicopter at the middle of the rotor system, this is what is known as the center of gravity, or CG. Once the allowed payload has been determined, it must be balanced. To maintain the safest flying characteristics, the pilot must balance the load on the helicopter. If the CG is too far to the rear or aft, the helicopter flies with a nose-up attitude. If the CG is too far forward, then the nose tilts down. In either case, controlled movements are difficult, and maneuverability is decreased. The same is true for lateral CG, or side-to-side loading. All weight should be evenly distributed. If in doubt, ask the pilot where to sit or place and secure all cargo. We have just covered the flight controls, aerodynamics, hovering in and out of ground effect, emergency procedures, weight and balance, and density altitude. These topics comprise a helicopter's capabilities and limitations. Remember, you play a key role in the safety and success of each mission.